In today's lecture, we will consider some power conditioning circuits using power electronic devices, namely diodes and thyristors. These devices, in fact thyristors, are used right up to very high power levels of the order of thousands of megawatts in HVDC systems. But in general, power conditioning circuits are also used in low voltage circuits, right from a mobile phone charger to the power supply of your computer to motor drives and many other applications. Now, power conditioning circuits we began last time by considering a simple diode and its characteristic. So, we will quickly go through it and look at some of the important circuits. Okay. Now, we saw last time that we could, this is the characteristic of a diode, and the reverse voltage breakdown voltage VBD is quite high, and Vf on the other hand is small, and the slope of this curve in the forward direction is extremely high. So, it has a very large conductance. Remember that we are having an IV characteristic, I on the y axis and V on the horizontal axis. To solve circuits with diodes, if one takes a nonlinear characteristic, then solution of the circuit would require us to solve the circuit using an iterative method, that is Gauss-Seidel method or Newton-Raphson method. But the other approach is to essentially model the diode as an on-off switch, and the last time we saw that the way towards that is first assume that this slope is very large and make it a straight line. So, that it's kind of a linear approximation of the slope, and also below Vf we assume no current flows, and in the reverse direction current is actually 0. So, this actually 0, I mean in the model it is 0. So, this kind of model is in fact shown at the bottom here, you see that, and if we further approximate it, we can actually treat it simply as an on-off switch. So, in the previous model you can have essentially a voltage source Vf in the forward. Whenever it is conducting, it behaves like a forward voltage Vf appears across the diode, but you can even neglect that in many of the analysis where high voltages or voltages above 100 volts are applied. You can actually neglect that Vf, and you can in fact get a interesting. So, as at least as a first cut analysis, or the first time you do an analysis, you can treat the diode as simply an on-off device. That is, when voltage is positive, it turns on, it has 0 impedance or 0 resistance, and when the voltage is negative, it has 0 current flowing through it. So, the simplest of course circuit, power conditioning circuit which we learned probably in high school was this is called a rectifier circuit, but a half wave rectifier, and the diode conducts in the forward direction. It is on, the switch is on, that is it has 0 impedance in the forward direction, and when the voltage across the diode is negative, then you will have in fact that switches off, and you will find that there is no current flow in the reverse direction. So, current flow in the reverse direction is blocked. So, this is, you can look at it this way, and you will see that if the voltage across the diode is positive, that it is forward biased, it switches on, and it switches on right at this instant, because here the forward voltage is applied, and then you have got this it follows the input waveform till this point, but from here on it cannot conduct in the reverse direction. So, you have got effectively a half wave rectified waveform. Now, you can actually make it, you can in fact, you will see that it conducts only in half a cycle, but you can make a simple modification to this circuit and get a rectified waveform which is looks somewhat more like DC. In fact, here you have got every alternate half cycle the diode conducts, and so of course it has got a DC component, but a significant harmonic component as well. So, the output waveform on the DC side is what is shown in black here, or what is shown in blue, and you know that this is in fact a a periodic wave, and it has got a fundamental DC, a fundamental second harmonic, and so on. But the important thing, it has got a DC component. Okay. So, it has got a DC component and significant harmonic components as well. So, in fact, you can get a better kind of DC. It's DC would mean, of course, your idea of DC would be a straight constant, but here we mean that it is a non-zero average value. Okay. So, we can actually modify this circuit in this fashion. What we do here is, of course, break this source into two parts, each of half of V in, and what we do, how can we actually obtain this voltage? It is essentially, you can use a transformer, you can actually get, you can apply the voltage V in, and using a transformer you can get, in fact, half of V in and half of V in. Of course, if you measure the voltage in the direction shown by the arrow below, you will find that the potential drop in this direction is minus 0.5 V in. Okay. So, this is essentially how you can implement it. This is in fact one interesting place where you can use a transformer. It will also give you isolation, that is, you can, if you wish, to ground this point even if the source is grounded as well, without affecting the operation of the circuit. So, in fact, so what we have done in fact is something like this. So, what we have here is this split into two voltages of equal magnitude, and what we are using this transformer achieved this. So, this point with respect to this point, the voltage is minus point. So, there is a minus sign here. So, this point with respect to this point. So, this middle point is called N on neutral, okay, of this circuit. So, what you have essentially is a simple diode circuit. Now, if you use this circuit, what is the thing which we have achieved? We in fact get a full wave rectified waveform. Okay. Now, you get a full wave rectified waveform, but of course, the magnitude of this is 0.5 V in, the peak value, unlike the last time where it was half V in. But if you notice that this rectified waveform will probably, intuitively speaking, you can easily show that the harmonic component as a ratio of the fundamental or the average value is going to be lower. So, if you take the average value of this waveform and you check up, if you kind of group all the harmonic components, then you will find that the average ratio of the average component to all other harmonic components is in fact quite high. So, the average value is high and the ripple is lower. So, put it in other words, the ripple is lower in this waveform. But of course, the voltage V in is, the peak value is half V in. If you look at this example, of course, here I assume that this transformer had a 1:1 ratio. So, this so what if this is if the number of turns here says 100, then that winding will have 50 and the bottom winding will also have 50. This is something which I did not mention here. Now, if you take another circuit, that is a rectifier, but what I do now is I reverse the polarity of the diodes. Let us just look at the previous slide, and now what I have done. And if you do that, the nature of the waveform at the output V out in the polarity is, of course, the potential of the top point with respect to the bottom point. That voltage is in fact negative. So, you will get a negative voltage here, and the current IR also will actually will also have the same waveform, and also will be negative, with IR shown as with the reference direction in the way it is shown. The current will in fact be negative and will follow the voltage waveform. Okay. Now, if you take these two circuits together and flip this circuit at the bottom. So, what I am going to do is take, suppose these are two identical circuits and I flip this, and what you will find is, of course, that this is like R, and what I will do is I will flip this circuit. So, actually this is more convenient to do. So, R, and what I do here is I flip this circuit. and have this like this and merge it with the circuit given above. So, you have got this source here and this, and this is how it goes here. Okay, this we will have to ignore this portion. Okay, that is fine. So, what we will do is merge these 2 points, and if you do that, you will in fact have a common point here, and here you have got this and this here like this with a source here. Yeah, that is okay. Source here and it is like this, and this is another. Just let us say these 2 wires are merged together. In that case, you will have this, this, so it will be this way, and this will be this way, and what will have it like this. Now, what happens is this current here is going to be 0, because this if you see the current IR here, and we will call this IR dash maybe, but if you take this direction IR here, so what flows here is IR1 plus IR2, but we see that IR1 and IR2 are in opposite directions, so this is going to be equal to 0. So, what happens is that you have got a circuit like this, and this source is 0.5 and this is minus 0.5, this is 0.5 and this is minus 0.5. So, actually you can simply connect it this way. You do not have to have this neutral connection anymore, because this what I call the neutral is of course this return path here. You do not even have to have it, and because these sources here are again similar, you can in fact have this connected in this fashion, and this is in fact a bridge rectifier. So, now you do not of course have to separate out the sources, because the neutral, there is no midpoint connection here from the source, and therefore, you have in fact got a bridge rectifier which has got this waveform. So, now of course, you have got full voltage appearing across this resistance. So, actually this is a interesting kind of circuit, it is called a single phase full wave bridge rectifier, and extend this analysis. In fact, in this earlier case, if you look at this rectifier, you have got 0.5 V in and minus 0.5 V in, these actually 180 degrees apart, you can say the waveforms. You can with 3 phase have 3 voltages which are 120 degrees apart, and in that case whenever VB for example becomes greater than VA, you will find that this diode D2 will be forward biased in case D1 was initially conducting. So, in fact, you will find that diode D2 will conduct and D1 will switch off, because the voltage across will go negative. So, you no longer have forward voltage. So, actually you will find that whenever each of these waveforms here VA, VB, VC individually become greater than the other waveforms, you will find that that particular diode will conduct, and the waveform therefore will be of the nature shown here. This is called a 3-phase half wave rectifier, and the waveform in fact looks a bit different from the earlier case, and wherever you find that a particular voltage, say VB becomes greater than VA, at that point the diode D2 conducts. So, D2 conducts in the place where it is shown here, then D3 conducts in this region, and so on. Okay. Now, you can extend the analysis which we did, we can convert this into a bridge rectifier, and if you convert it into a bridge rectifier, this is a 3-phase full wave bridge rectifier, and this rectifier circuit will have nice waveforms. So, the voltages, the average voltage is higher, and you will find that the ripple also is very low. In fact, this ripple will be the lowest order harmonic in this is the 6th harmonic. So, you will have a 6th order ripple, the ripple will be 6th, 12th and multiples of 6. So, the harmonics are multiples of 6. We also have a voltage rectifier which has got this, usually if you put a capacitor at the output, you can actually hold the voltage for some additional time. For example, if you go back, we will just go back a few slides and look at our full wave bridge rectifier. Here the voltage at the DC side follows the AC side voltage, but if you have got a 3-phase bridge rectifier, of course, you find that you have got a nice ripple free, rather not ripple free, but low ripple kind of DC voltage waveform on the DC side. And but in case of a single phase bridge rectifier, you can get lesser ripple by putting a capacitor. A capacitor is a device which draws current whenever there is a change in voltage, and one of the ways of describing the action of a capacitor, it tries to prevent a voltage change across it. Actually, it does not try to change. As soon as the voltage changes across it, it draws a current. So, but you will find that its action in many circuits can be described in this nice way. Similarly, an inductor is a device which the voltage across it is proportional to di by dt, and you can always one of the ways in which its action is described, it tries to change the tries to prevent a change of current across it. What it actually does is that whenever the current changes through it, there is a voltage across it, and the effect of the voltage may be in fact to reduce the rate of change. So, similarly here a capacitor also plays a similar role. It draws a current whenever there is a change of voltage across it, and in fact in case the diodes D1, D2 or D4, D3 are conducting, by KVL the voltage across the capacitor is equal to the voltage across the source. So, voltage across the capacitor is equal to the voltage across the source if these diodes are conducting, and these diodes will conduct provide the voltage across them is positive. So, actually if you look at the waveform of a rectifier, bridge rectifier, full wave bridge rectifier, the capacitor, you will find that in the regions where the diodes conduct, so that region where the diode conducts, your voltage across the capacitor actually follows the input voltage. At this point, in fact, the diode stop conducting and the capacitor discharges into the resistance. So, of course, if the capacitor is large enough, the rate of discharge is slower. If the capacitor is large or this resistance is large, so either of these two things happen, the rate of discharge is low. It is shown as a straight line, but actually it is slightly exponential. It is kind of a RC decay. So, this kind of so if R or C are large, you will find that the decay is not much. The time constant RC is in fact quite large. Now, one of the interesting things about this circuit is that diodes do not continually conduct, in fact continuously conduct, they for some part of the cycle they are not conducting. Another interesting point about this circuit, which is very simple, in fact, you get a reasonably low ripple despite having only a single phase bridge rectification. One of the interesting points is, of course, is that you are connecting a voltage source across a capacitor, although it is through diodes. So, if you just suddenly switch on this voltage source to an uncharged capacitor, it is possible, if the voltage is of the source is different from that of the capacitor, say the voltage is some positive value, the diodes D1 and D2 will conduct and charge the capacitor, but that current will be extremely high, because you remember that you can't actually connect a voltage source directly across a capacitor, because the capacitor voltage, if it suddenly changes, so if a capacitor is not charged and you connect a non-zero value of voltage across it, there will be an infinite spike, in the impulse in the current. Of course, this is limited, you do not have an infinite impulse, because it is limited by the resistance of the connecting circuit as well as the stray inductances of the loops which are formed. So, what you will find is, in fact, you have got a large current, and you would have noticed this when you try to connect any power supply which has got this kind of circuit at its front end. So, this is regarding a diode. Just as a brief aside, that in case you have got a solar cell, in a solar cell, in fact, if you have light falling on the solar cell, you will find that the VI characteristics of the cell get slightly will get profoundly modified. In fact, if you look at the kind of impact it has, because what happens is that when light falls on the diode, its characteristic goes into this quadrant, the fourth quadrant here. So, what you have is that you can have negative current and a forward voltage, So, this actually negative current when you take the reference direction as shown here. In fact, in this quadrant the diode in fact in a way is actually generating power. So, this is in fact used in solar cells, these kind of diodes. In fact, this is a typical. So, what I have done is of course reverse the direction of IAK, and therefore, this portion of the characteristic comes now on the top on the first quadrant, and this is the characteristic, and of course, this characteristic depends on the amount of light falling on the solar cell. So, you will find that this is a typical characteristic of a solar module in fact, which consists of many solar cells. If the amount of radiation following is 100 watt, 1000 watt per meter square, then you can get around a power of almost 300 watts if you are operating at the corner point here almost. Okay. So, you can in fact, so this is the characteristic. What point on this curve you will be operating really depends on what you have connected to the diode. So, if the diode is just connected to a resistance, then you will find that wherever the IV characteristic of a resistance, which is a straight line, intersects this curve, is the point at which you will operate, and that much power can be actually delivered to that resistance. So, this is what a solar cell does, it converts the light energy into electrical form. The other device which is of importance is a thyristor. A thyristor actually gives you 1 degree of control. So, in fact, this has got another terminal called the gate, and the thyristor in fact, if you give a gate current, if a gate current flows through this and the thyristor is forward biased, then it goes into what is known as the forward conducting region. So, this is in fact the forward conducting region of the thyristor, but in case you do not give the gate signal, actually it blocks the voltage, has no current or very little current in the forward direction. So, typically the forward voltage VFD can be quite large, and it also BD, which is the reverse breakdown blocking region voltage, is also quite large, but in case the thyristor conducts, then the forward voltage is like a diode. So, the behavior is almost like a diode. So, as long as you give the gate signal. So, what is the advantage of this? A thyristor can be controlled unlike a diode bridge. A diode can switch on whenever the voltage across it becomes positive. There is no other control, it is completely dictated by the conditions in the circuit to which it is connected to. Here you have got a degree of freedom, even if you are forward biased, if the circuit on which this thyristor is connected, or across which the thyristor is connected, the voltage VAK is positive, the thyristor will not turn on unless you give a forward signal. So, unless you give a signal at the gate. So, that is 1 degree of freedom you get. That means that you can actually control the output, and that is what we shall see shortly. So, in fact, this is one of the kind of a data sheet. In fact, for all these devices, these are commercially available. You can actually go to various manufacturers and see that the basic performance features of this characteristics of these thyristors are given in quite a bit of detail. In fact, they will give you with respect to the currents and the temperatures, the forward drops, and also the forward or reverse blocking voltages. So, this is one thyristor which has got a blocking voltage of 1200 volts. So, this of course can be used for general purpose our 230 volt supplies quite easily. So, this thyristor can be used in conjunction with circuits in which the forward voltages or the reverse voltages across the diode do not exceed this value. Okay. So, now what we have additionally in this circuit is in fact a trigger circuit. So, the trigger circuit actually gives a signal to this thyristor. If it is a light signal, then the trigger circuit in some ways is isolated from the main power circuit. So, it could be a light signal, but in case you are sometimes what happens is that you do derive the trigger circuit is in fact an electrical current, and in that case of course, you need to have a closed path for the current to flow, and usually the trigger circuit derives its power supply from the voltage across the thyristor itself. So, the voltage here is fed to this, and you have an electronic circuit here which actually generates a current which goes into this the gate and switches the thyristor when it is forward biased, when you wish it to. So, you wish it to is of course means that there is some control, and this is in fact got from some control circuit which tells you what point you should fire the thyristor. So, this is what is known as an electrically triggered thyristor, where your power supply for the trigger circuit is also derived from the voltage across the thyristor, which actually the trigger generates a current which flows through the gate, and this in fact flows into the trigger circuit as well. So, this is essentially a trigger, and the trigger is actually fed by some signal from outside. For example, you could have some way of conveying to the trigger circuit that you should trigger the thyristor at a certain point, and that is usually done through some mechanism like for example, a variable resistance or a pot which tells you, okay, you figure by giving some kind of control signal. Okay. So, that is something which you have to derive separately. So, this is a control signal which could be given manually or coming from some other circuit as well. Now, if you on the other hand have an isolated trigger circuit, this would be a light signal which turns on. So, this is called a light triggered thyristor. So, in that case you have got an isolated circuit. This circuit the potentials here have been using a transformer or optical coupler, this can be at a different potential altogether. Okay. So, this kind of thing can happen, but in case you have got electrical triggered circuit. So, if you have got this, if you have got an electrically triggered thyristor, then the supply of this is actually derived from this, but of course, this may contain electronics which themselves require power supplies. So, usually you will be using some kind of transformer here for isolation purposes. Okay. So, that this circuits potentials do not for example, if this is a circuit with this is grounded, then if the electronic circuit also has to be grounded, but you do not want, you wish to have freedom in which point you want to ground the electronic circuit, then you would require an isolation transformer. Okay. So, this is an important point which you should notice. So, if you have got a trigger, what can you do with it? The thing is that if you have got a trigger circuit and you have got some control in the thyristor, you can delay the operation of the thyristor. So, remember that in a reverse bias condition, the thyristor behaves like a diode. What essentially we can do with this thyristor is that unlike in a diode rectifier, you can actually delay the firing of the thyristor. So, in fact, if you have got a half wave rectifier, then you could have in fact you are forward biased right at the initial point here, but you can delay the firing by a small amount, that is this alpha. So, this is the firing angle, and now the waveform, if you have got a resistive load, looks like this. If you had an inductive load, of course, you can have a slightly different behavior. For example, if you got an RL circuit, this is 0 as this will be 0, and here the current would increase, and in fact, it will not suddenly become 0 at this point, but here the thyristor will stop, because here the current reaches 0. Okay. You can't switch this off here, because although the source voltage has reversed here, the current is still positive. Okay. So, because it is positive, if you have got an RL circuit, so remember that what I am showing is that in case you have got an RL circuit, then this is the waveform. So, your current will in fact go down to 0 afterwards. You can't switch off here is the source voltage becomes negative, but the current is slightly, you can perhaps call it lagging the 0 of the source voltage, and you can't switch this off suddenly. An inductor, as I mentioned some time back, prevents a sudden change of current through it. So, if the current tries to suddenly change, then for example, if there is a current flow like this and you suddenly try to switch it off, a voltage here, large voltage appears here which tries to keep the thyristor still conducting. Okay. So, in fact, your current when in fact, this is the point at which the thyristor will switch off. If you have got on the other hand an R load, what you see in blue is the response. Okay. So, this is essentially what is the response. So, the inductor, by putting in RL load, you in fact are making the current stay on in despite of the fact current still despite of the fact that your source voltage is negative, the current can still continue. If you have got an extremely large inductor, then your current would rise also very slowly and also go down also very slowly. So, in fact, it will go like this, and in the limiting case you can also think of having continuous conduction. Okay. So, it depends on the value of L. Okay. Yeah. So, if you look at this, this is a bridge, Thyristor bridge rectifier, and the waveform, you will see that the waveform now looks like this. If you got an R load, the voltage and the current waveforms are identical, but if it is an RL load, then depending on the RL time constant, you will find that the current may continue for some time, and in fact, you can as I mentioned sometime, if you start the bridge in this fashion, you may actually have a current which is like this and like this, and eventually it will reach some steady state. I have not drawn it very well actually, yeah. So, something like this and like this. In fact, the RL circuit acts like a filter and then it reaches some kind of steady state. So, in fact, the RL circuit is like a filter. You know that RL circuit has a transfer function between voltages and resistances 1 upon R plus SL. So, higher frequency, in fact, there is attenuation. So, that explains why if you have got an RL circuit at the load, your ripple is much lower, because the higher frequency harmonics get attenuated in the current. Okay, yeah. You can also have the other kinds of circuits with thyristors, and this is called a thyristor controlled rectifier reactor. So, reactor is another word for an inductor, and in case you have got a back to back connected thyristor, you could in fact fire it in a certain way. For example, you can delay the firing to, so this is the input voltage, and if you can fire the thyristor at this point. Okay. This is the exact when it reaches 90 degrees you fire it. So, you will find that the current increases, the current through an inductor is the integral of the voltage which you see across it. So, if you integrate this voltage waveform from this point onward, you will find that the current is increasing. So, the current is equal to 1 upon L times the integral of the voltage. So, you will find that in fact, this voltage is you have to integrate this voltage. So, if you integrate this voltage, and scale by 1 by L, you will find that this is how the current increases. It reaches a peak here the voltage starts decreasing. So, if you integrate it now, the current is going to drop, and because the voltage becomes negative, integral V dt implies a decrease in the current, and because of this the current will drop here. So, this is if you delay the firing by 90 degrees. In fact, it is behaves like just like a normal reactor or normal inductor connect. So, if you had removed this, so this thyristor T1 and T2, so thyristor T1 conducting here and T2 conducting here are continuing alternately conducting for 180 degrees, and you will find that you get a continuous voltage waveform, current waveform which lags the input voltage waveform. So, it behaves like a normal reactor in case your firing angle is 90 degrees, but in case you increase your firing angle, if you increase the firing delay angle. So, now what I am doing is this thyristor T1, I fire it at something greater than 90 degrees. So, greater than 90 degrees here from this voltage 0 point. Now, if you integrate the voltage, you will get a current which is this, because the voltage is negative, the current will decrease, and actually this is the thyristor T2 which will switch on. So, I will give the firing signal to thyristor T2 after 90 degrees of this 0 crossing. So, now you will have a negative current, and from this point onwards it becomes positive. So, this current starts increasing again like this. At this point the current becomes 0 and the thyristor stops conducting. Okay. So, the thyristor stops conducting when the current through the inductor becomes 0. And now it switches on again. Here in fact, now the firing angle has been again given greater than 90 degrees. So, what have I achieved? For example, if I give a firing angle greater than 90 degrees, you will find that your current waveform is like this. Now, this is an AC waveform, but it has got, it is a periodic waveform, alternating waveform, but it is not a pure sinusoid of one frequency. You can again use Fourier analysis and show that it has, this waveform has got a fundamental and harmonic component. In fact, the fundamental component will be, suppose this is the voltage In fact, I have not drawn it very well, but suppose this is the voltage, then the fundamental component of this current is going to be in fact like this, the fundamental component. So, the fundamental component is going to be like this. Now, this is something you can actually get through Fourier analysis. So, you will have a fundamental component. So, the fundamental component of this bumpy waveform here is actually 90 degrees lagging the voltage. So, the fundamental component of this, that is, or you can say the first or the fundamental component is 90 degrees lagging. It does not, if you fire it symmetrically on both sides, then it does not have a DC component. And it also does not have even harmonics. This is something you can try to infer. So, if you have got a symmetric bumps on both sides, that you fire both thyristors symmetrically T1 and T2, which is not the case here, because here I have fired it asymmetrically. But in case you fire it symmetrically, in that case the fundamental, you will have a fundamental component of course, but you will not have any DC or even harmonics. And the fundamental component is very easy to show, that will be 90 degrees lagging the input voltage. So, what happens is effectively is that you still, this device which is thyristor controlled still behaves like a inductor, but it is a variable inductor, because if I change the firing angle, let us say now I change the firing angle and I advance the firing angle a bit. Now, the fundamental component will change, because I have changed, from this I have become this. So, the fundamental component, when you do the Fourier series waveform, Fourier series expansion of this wave and the Fourier waveform of this wave, you will find that the fundamental component of this waveform here, the top one here, which I can give by some other color perhaps, the top waveform here, this waveform, the fundamental component will be larger. So, actually what it means is that depending on the firing angle, you can change the nature of the waveform. Well, I would say the nature of the waveform change is almost is practically the same, it is a kind of half bumps. You can, but the fundamental component of that waveform can be changed. So, you can vary right from this delay angle being 90 degrees, as in this waveform, to the delay angle being quite small, like here quite large, sorry, where it is nearly 180 degrees from the 0 crossing. So, you are firing it here. So, this distance is more than 90 degrees, almost near 180 degrees. If you are nearer to 180 degrees, the fundamental component of the current is much smaller. Okay. So, actually what it means is that you have got a device, if you just look at the fundamental component, you have got a device, this whole device which is a TCR, in this particular device the amount of current drawn, the fundamental component is 90 degree lagging and its magnitude of the fundamental depends on the firing angle, delay angle alpha, and alpha can change, this is alpha can change from 90 degrees to 180 degrees. If you are at 180 degrees, there is no conduction, because you are firing it at this point. When you integrate this point, there is no current will be there, because the voltage is just 0 here. So, you will have maximum, you will have the maximum amount of current in case it is 90 degrees conduction, and minimum conduction when it is 180. So, you will have in fact, so this is a variable, you can say it draws a variable current depending on what alpha you give, and rather I should say you can change the current drawn, the fundamental component of current drawn by changing this alpha, and therefore, this acts like a variable inductor. So, it is called a thyristor controlled reactor, and this particular device TCR is actually connected in shunt in power systems to in fact control the, in fact you can control the reactive power drawn by the device. So, this is useful in voltage control, a thing which we shall study later on in this course. Now, coming back to thyristor AC to DC conversion, in fact, we started off with a rectifier circuit and then went to a thyristor control reactor circuit. We will come back to a rectifier circuit. Remember, at a rectifier you have got in fact a set of switches which connect A to the output O O1 or O2. So, if in fact if VAN is positive, then A is connected to O1. If VAN is negative, A is connected to O2. So, you actually have the rectifier or a bridge rectifier does that. It tries to connect some point the A point to O1 or O2 depending on the voltage which is there. Okay. So, this is essentially something which we can use to understand a 3-phase bridge rectifier. We already have understood it for a single phase case. Now, we will go ahead and try to understand it for a 3-phase case. So, if you look at a 3-phase waveforms in phasor form, then you will find that we will assume here of course that the we are considering a 3-phase rectifier. It is also called a 6-pulse converter. The switches are ideal. Okay, we treat them as on off switches. The AC source is infinite. Actually, the correct more appropriate way of saying it is that the source impedance, it is a good voltage source. So, it does not have a source impedance or there is no drop across it when a current flows through it. So, this we assume it is a ideal voltage source. Okay. And on the rectifier output side, we will connect not a R, but an R, L and E circuit. So, this is something I shall show to you shortly. Yeah. So, this is what I am going to. So, you have got a source which is actually ideal voltage source. On the DC side, you have got an RLE. R of course is the winding resistance of this inductor. Okay. So, but this inductor is assumed to be very large, and if the inductor is very large, as I mentioned some time ago, it smoothens out the current. The current kind of remains continuous despite the switchings, and you can use the property of an inductor that it tries to attenuate fast changes in the current. So, what you have is, or rather if there is a voltages across it, for example, if this voltage V naught, which is the input voltage of the to this RE circuit is varying fast, the current will not vary that fast, because remember that a inductor tries to oppose fast changes in the current. Okay. So, that is one way of describing inductor action. Now, if you take this kind of circuit, there are now 6 thyristors. They are numbered T1, T2, T3, T4, T5, T6, but in fact they are not numbered spatially that way. The reason is that the subscript has been chosen in the sequence in which these thyristors in fact are turning on. The voltage, line to line voltage is appearing across each of these phases here, or the phase to phase voltage or the line to line voltage is √3 times Vm. Vm is the peak value of the phase to neutral voltage. Okay. We will assume that the neutral here is open, there is no fourth wire. So, this is just an open neutral, and what we of course should realize here is that the voltage VAB in fact leads VAN, the voltage VAN by 30 degrees. This is something we had learnt of when we understood 3-phase circuits. Now, in case you have got a bridge like this, of course, this R I had not shown earlier, but this R is a very small R, let us say. So, it is mostly an inductive element on the DC side. In that case, you will find that initially this is the circuit. If you continuously if the thyristors are permanently, of course, this word permanent has got deleted, but the point is that if you continuously provide the gating signals to a thyristor, it in fact behaves like a diode. So, what you see here is of course that what the waveforms when the thyristors are fired continuously. So, it behaves like a diode. So, in fact, we have done this circuit before, it is a 3-phase diode rectifier. So, you have got the lowest harmonic component on the DC side voltage is in fact the 6th harmonic, and 12th harmonic and multiples of 6. The lowest harmonic is of course the 6th harmonic, that is, if you have got a 50 hertz input AC waveform, you will have 300 hertz as a minimum harmonic which appears. So, you have got DC because there is an average value here, but there is no fundamental component, there is no 50 hertz component, but directly a 300 hertz component, 600 hertz components and so on. This is not surprising because this is periodic with a period of t by 6, where t is the fundamental period of the 50 hertz waveform. Now, remember that if you have got a 3-phase bridge diode rectifier, each diode turns on just when it is forward biased. So, in fact, you will find that T1, T6, all of them turn on just at this point, okay, because the thyristor which is continuously fired is in fact like a diode. Another aspect which is interesting is that when thyristor T1 and conducts, then the current IA, this current IA here is equal to the DC side current. If this inductor is assumed to be very large, the current DC side current is in fact a constant. So, that is what we have in fact assumed here, that there is hardly any ripple in the current. So, it is a constant on the DC side. So, what you will find is that the current on the AC side IA is in fact a constant as long as is constant, and the DC side current flows from IA as long as this thyristor T1 is conducting. Okay. So, as soon as thyristor T1 stops conducting, you will not have IA is equal to IDC. In fact, for some while, for some time, in fact, neither thyristor T1 nor thyristor T4 conduct. In that case, there is no current in this wire here. Okay. So, what you actually see is that this conducts for 120 degrees as long as T1 conducts, and when T4 conducts, remember that since it is the bottom diode, the current IDC minus IDC is equal to IA. So, if IA is in the direction shown here, the arrow is shown on the left hand side. Yeah. So, you will find that this current IA is equal to minus IDC in case T4 is conducting. So, the waveform is in fact what is known as a quasi square wave. It is not a square wave. A square wave would classify as a waveform of this kind. So, you in fact this is a square wave. This is in fact a quasi square wave, that is it is like this. Okay, on this side this is 120 degrees, this this is 30, this is 30, this is 120. So, you have got this is 30, this is so the waveform is actually 30, 120, 30, 30, 120, 30, this kind. This is a quasi square waveform, and it is very interesting that this waveform does not have third harmonic. So, this waveform you can do the Fourier series and see that if you have got a waveform of this kind, this is in fact this total duration is 60 degrees, this is 120 degrees, this is 120 degrees. And in fact, if you look at this waveform IA, the fundamental component of this waveform will have, if you use a Fourier series and compute the AN and BN terms, that is the cosine and sine terms, and redraw the fundamental waveform, only the fundamental component of the waveform, it will have a waveform like this. It goes down to here and then like that. Okay. So, I have not drawn it, it does not look like a nice sinusoid, but you get the idea, I hope. So, this is the waveform which you get, and if you look at this waveform here, this is 30 degrees, this. In fact, this voltage here, so this is in fact VAB, and you will find that in fact IA is in phase with VAN. So, the IA, the fundamental component of IA is in phase with VAN. Okay. Now, in case you give a delay, like you delay the firing by 30 degrees, that is you have given instead of firing at this point as in the previous waveform. So, if you go to the previous waveform, it is fired here, now it is fired with a delay. So, this thyristor continues to conduct till this point where T1 is switched on. So, T1 takes over from the earlier thyristor, which is the thyristor which is in fact T5. So, T1 in fact is taken over by T5 is taken over by T1. So, what happens is this is conducting and then this takes over, okay, because this gets forward biased, and as soon as you switch this on, this will get reverse biased. So, that is the basic idea. So, what happens is T1 takes over from T5 and T1 and T6 conduct, and eventually what you will find is one interesting thing which has occurred is, if you switch on the, is that this in fact now has moved slightly here. This is the current waveform. So, if I've got a firing delay angle of 30 degrees, the current also has moved 30 degrees. So, the fundamental here also, the fundamental lags, the fundamental component of IA, I will call it IA fundamental, lags VAN by this 30 degrees. So, you can say the power factor, if you neglect the harmonics, the power factor in fact of the waveform depends on the firing angle delay. So, this is the AC side current, remember. So, this is the AC side current. If you look at the valve voltage waveforms for the thyristor T1, the voltage across the waveform is positive from this point of time, but because you are having a delay angle, you fire it only here, although it is forward biased. As long as it is conducting, it is 120 degrees conduction, as long as it conducts, the voltage across it is 0. As soon as it stops conducting, that is some other thyristor takes over, your voltage across the valve increases, okay, it changes again, it is a reverse voltage. So, it stays reverse biased. So, now one interesting point here is, of course, here we are assuming that the DC side current is constant. So, this is something which you should remember. So, IDC is remaining constant. So, this is IAC of course, but IDC is constant. Because IDC is constant, IDC is constant because the inductor on the DC side is assumed to be very large. So, even though the voltage which is applied to the inductor has got DC and a ripple, the ripple voltage does not cause a ripple in the current because the inductance is extremely large. So, because the inductance is extremely large, it filters out or attenuates the high frequencies. So, what you find is the current will not have much of a ripple. The current is dictated mainly by what you have is the the R of the circuit, okay, and the average value of this waveform. Now, you can have 60 degrees conduction here, and further you can also have 90 degree conduction, but if you actually have 90 degree conduction, in that case you will find that the instantaneous voltage becomes negative. And another thing is that at 90 degrees the average value of the waveform is 0 at 90 degrees. At 60 degrees it just touches this 0. So, if your firing angle goes beyond 60 degrees, in fact the instantaneous voltage can be negative for some part of the cycle. So, one of the important points is that what is the average value of the voltage which appears on the DC side. In fact, a little bit of calculus will tell us that the average value which we get by integrating the voltage during the conduction period is in fact Vd0 cos alpha, where Vd0 is equal to 3√3 Vm by pi. So, Vd0, just easy to remember, is 1.38 times the line to line RMS voltage on the AC side. So, of course, Vm here is the peak value of the phase to neutral voltage. So, Vm here is the peak value of the phase to neutral voltage, yes. So, what we see in fact is that alpha is in fact, if alpha is equal to 90 degrees, then Vd0 becomes V output, the DC voltage has got an average voltage which is 0, okay. And if alpha is equal to 0 degrees, you have got maximum voltage, okay. Now, one important point which you should not forget in all this analysis is that we are assuming here that the current on the DC side is constant, okay. Now, of course, this aspect and constant and in a certain direction, it is in one particular direction. So, this aspect has to be revisited again when you come to angles which are larger, okay. Now, if you look at a thyristor bridge, Let us replace it by some box here, a kind of black gray box here. And one of the important things which you should remember, because the thyristors never conduct in the reverse direction, IDC can never become negative. But can VDC become positive or negative? The answer is yes, because it appears from the equation which we saw in the previous slide. If alpha is greater than 90 degrees, the DC voltage can in fact become negative. So, DC voltage can in fact become negative, but IDC cannot become negative. Now, there is an important caveat here, because VDC can be negative under one, it cannot always be negative. There is it can be negative provided the current is still in that in the direction shown there. Okay. So, at any point if the current becomes 0, then the thyristors stop conducting. If the thyristors stop conducting, then you in fact we have to revisit what kind of waveforms you will get. Okay. So, all the waveforms shown so far assume that on the DC side you have got a positive current IDC. Okay. So, if you have got a positive current, then this formula which I gave before is valid. Okay. Yeah. Positive and continuously positive, I mean it should not become 0 in the middle of the cycle, okay, at any point in the cycle. Now, the point is here the question which arises is, if this VDC is negative, that is alpha greater than 90, can IDC be in this direction? So, for example, if you got a RL circuit and you apply VDC here, VDC is also called V0 in some of the earlier slides. So, just to there has been a double notation here. But suppose this is VDC, which is the output of the rectifier, and VDC goes negative. What is the direction of the current? Well, the current is given by in steady state is determined by the resistance of this winding. So, what you have here is the current is VDC by R in this direction. In fact, it is VDC, suppose there is a source also here which I shall call V dash, then you have got the current flow IDC in steady state is equal to VDC minus V dash by R. Now, the question is that if V dash is positive and VDC is negative, there is no way in steady state that the current can still flow in this direction. So, what we have essentially is a situation that, so if I am going to have alpha greater than 90 degrees, VDC will be negative, I told you, only if the current is continuously conducting. If the current suddenly stops and becomes 0, none of these thyristors will conduct. So, none of these thyristors will conduct in case the current here becomes 0. Okay. So, if there is a negative voltage, current will try at least to reduce and go in the negative direction, but that is not allowed by these thyristors. So, how can you have VDC negative? There is only one way you can have VDC negative, that is if you go to the next slide, it becomes apparent. What if your voltage V dash is in this connected in this direction? I have shown it as V0 here with a straight sides, this is nothing but V dash what we used earlier. If I have got a source on the DC side which pulls the current in this direction, despite the fact that V naught is negative, then we can actually operate with alpha greater than 90 degrees and still have current flow in this direction. So, the only way you can have current flow in this direction and V naught being negative is to have another source which is connected in this direction. So, you can in fact have steady state operation with VDC negative only if you have got another source which still keeps the current flowing in this direction, and the polarity of this source should be as shown here. Okay. Now, so this is called inversion operation. Inversion because the current direction is like this, VDC can be negative if alpha is greater than 0. So, in fact, when VDC is negative or this curly V naught is negative with I in the same direction, you are in fact taking power from the DC source and giving it to the AC source. Where is it coming from? It is coming from this source. So, this source in fact is the source of the power for inverting mode, and if you want to go into inverting mode, it is obviously going to be true that you should have in fact a voltage source of the appropriate polarity on the DC side. So, power is of course in the inverting mode going from this DC side to the AC side. Okay. Power is actually being taken out from this, real power is in fact being taken out from this and given here. Okay. So, this is inverting mode. Inverting mode is possible only if you have got a power source on the DC side, which of course makes sense, absolute sense. Okay. And the current is still in the same direction, voltage is reversed. Okay. So, if alpha is greater than 90 degrees, you can get negative voltage, have current still in the same direction, provided your voltage source is in fact you have got a source voltage which is in this direction. In fact, in a HVDC link, as we shall see shortly, this voltage is provided by the rectifier at the other end. So, this is something we will try to understand. So, if you in fact have alpha greater than 150 degrees, 90 degrees, you can have negative voltage across the DC link, and this negative voltage can be sustained provided IDC is in the same direction, and IDC is in the same direction provided you have got another voltage source which is pulling current in that direction. Okay. And this is called inversion operation. And the voltage across each valve is in fact has got this waveform. It is forward biased of course at this point, and you have got a current flow. This is the point at which the device is switched on, the voltage across the device becomes 0, and when it is switched off again the voltage is negative for a short while, but only for a short while, unlike a rectifier. Now, so if you want to in fact if you look at how a HVDC link operates, in fact one of the applications of Thyristor-based AC to DC converters is having a DC link or a DC transmission. So, you have got AC, you rectify it, convert it to DC using a Thyristor bridge, and then you have got a transmission line which is actually a DC transmission line. Current flowing through this is in DC, and the other end is an inverter which converts the power back to AC. Now, remember that the inverter is operated with alpha greater than 90 degrees. Because alpha is greater than 90 degrees, the potential of this point is, the potential of B point is higher than the potential of A point. So, this is what you get because alpha is greater than 180 degrees. Remember the direction of the thyristors now is this way in the bridge. Okay. So, what you have is this potential is higher than this potential because alpha is greater than 180 degrees. So, in a way the voltage across the DC, if you measure the voltage across the DC link like this, it is negative. Okay. So, the current is flowing, of course, the current is flowing in this way which is allowed, the thyristor allows current in this fashion and it can flow like this. Remember that this voltage is, this potential is higher than this potential, current will flow like this only if this VAR BR is greater than VBI AI. Okay. So, this is also true. So, this is positive, but this is a greater number than this. Okay. And in fact, this plays the role of the voltage source which we saw in the previous slide. This is in fact you can, if you look at the way things are, this is BI and this is AI, and this voltage is in fact what the rectifier voltage appears at the inverter. Okay. So, this is what you actually see here. Can you go back again? BI is the bottom of this bridge. This potential is higher than this potential in inverting mode, and this is in fact, this role is played by the rectifier. This voltage which you see here is in fact provided by the rectifier. So, this is in fact that voltage V naught here. So, the polarity if you notice is appropriate so that the current will still be in this direction. So, this is how HVDC link works. In fact, this is how it looks like for a 2-terminal system. This is the same thing what I have shown you before. Remember that VB is greater than VAI, okay, for an inverter with alpha greater than 90 degrees. One of the things I mentioned sometimes, some facts, is that alpha in fact lags the VAN by the firing delay angle alpha. So, alpha also, so in fact your current lags the voltage by an angle alpha, which is in fact the firing delay angle. So, in fact VAN, if you look at the phase relationship between VAN and alpha, it is in fact for alpha is equal to 30 degrees, you will find the fundamental component of the AC side waveform is also lagging by 30 degrees. So, this firing angle has an intimate relationship with power factor. So, that is an important thing. You neglect the harmonics here, and this is what it is. And so, what it really shows is in fact at the rectifier side the P is absorbed from the AC source and so is Q. Q is absorbed because the current is lagging the voltage, it is actually absorbing reactive power. In the inverter, alpha is greater than 90 degrees and you will in fact find that again although the direction of P is reversed, that is from DC to AC, your Q is in fact still being drawn from the source. Okay. So, a thyristor rectifier with delay angle control in fact operates as in fact always draws reactive power from both terminals. Another interesting point about this thyristor bridge is that the firing is actually orchestrated in some way in conjunction with the voltages which appear on the AC side. In fact, the AC side voltages, the commutation points, that is the transfer of current from one thyristor to the other occurs because of the source side voltage. We saw that in a diode bridge also. So, in fact, the source side voltage in fact the source voltages are in fact required to do the proper commutation of thyristor. Commutation means switching off and switching on. In fact, the firing instance or the switching on of the thyristors and switching off of the thyristors is actually possible only if you have got AC side voltages. By chance, if the AC side voltages are not present here, you will not be able to operate the thyristor bridge in the way which I have discussed. Okay. So, this is often called a line commutated converter. So, it requires line voltages. So, in fact, if you have got the inverter connected to a passive load, is connected to a passive load, that is no voltage sources on this side, you will not be able to operate it. So, in fact, this HVDC link or DC link cannot supply power from an AC side through this link to the DC side to the AC side on another end if there are no voltages on that side. So, if you have got a blacked out or a passive load on system on one side, the inverter side, you will not be able to supply it, because the firing of these inverters and the operation of this inverter requires these voltages to be present. If you notice these waveforms, in fact, all these thyristor switchings are in fact mediated because of are in fact orchestrated in some sense by the three phase voltages which are there on the AC side of that particular bridge. So, if you do not have AC side voltages, you will not be able to operate this inverter in the manner which I had mentioned. So, this is an important point regarding this line commutated converter based HVDC terminals. What we will do in the next class is actually look at a few more points related to this high voltage DC links, and rather than high voltage DC links, high voltage DC links are in fact an application of this thyristor based converters. Remember, I will use the word converter and depending on the context it can be a rectifier or an inverter. Okay. DC link as shown here is in fact a combination of a rectifier and an inverter. Is that okay? So, what we will see is a few other points related to the HVDC terminal, and then we will move on to another kind of converter called a voltage source converter, and that will kind of wrap up our discussion regarding power conditioning circuits. When I say conditioning, of course, I mean you are changing the nature of the wave shape. Okay. Also, you can in fact later on we will see as we see here also you can control the magnitude of the voltages on the DC side. Okay. And this can be used for control. So, with this we will stop this lecture.